So we've moved around. We looked at circles, and this is obviously a topic around conic sections. And today we are moving forward to look at a specific um, topic as pertains to a figure that is created when a circle is moved, and this is called the cardioid. So the figure cardioid comes from the Greek word cardia, which stands for heart, and it's because it's shaped like a heart, and I think that's why it's called the cardioid. Some of you might have heard about a cardioid microphone, and it actually derives from the shape we're about to look at. So if we do have a circle and we create points that are equidistant from one another along the circumference. So these points are equally spaced. And then we use each point as a center from which we draw a circle of the radius of distance from that specific point to a point opposite. Let's take point A. This point A could be here, it could be here, it could be whatever point you choose. And so if we draw a circle of the radius that spans each point to point A, for all these points that we've created, then we're going to create a very interesting figure. So let's jump ahead and go and do that. So we'll draw, we've drawn already this circle, blue circle, and then we're going to just draw all the circles as we've shown here. We see that the envelope that is created that covers all this circle is shaped like a heart. And that's why we have this name of cardioid. So a cardioid is simply this shape that we've created that envelopes all these circles, and the circle that we use to create these center points is called the base circle. So we're going to look at several properties of this shape, the cardioid, and then that will be a basis for other very interesting shapes that are quite similar to the cardioid, but this is an interesting shape. It's not quite shaped like a heart. It's more like a bean, or it looks like an apple with a stalk removed here. But let's see how we may be able to so let's continue and look at some of the properties of this cardioid. So we have a base circle, we have the cardioid itself, and point A, mark you, could be any point on that circle. So let's continue. We still have, we'll look at that circle, and then there's point A, and we have 2 points, right? So we have a 2 points. The point Q, lowercase q here, and uppercase Q, and these points correspond to those equidistantly spaced points. So we just decided to pick 2 of them. And then if we go ahead and draw a line that passes between through Q, small q or lowercase q, and capital Q, we are going to get an interesting thing. So we have a line there, and then we use each of these points to create the circles that we talked about, right? And so we have 2 points. They meet at point A, but also meet at point P. And we also know that our cardioid passes right. Our cardioid passes right on the point P and point A. So it's a very interesting thing we can begin to see here, right? So we have this line that passes between lowercase q and uppercase Q, and then we have our cardioid that's created by the envelope around these circles. And we see that these circles here intersect at point P and at point A. They seem to be, these 2 points seem to be mirror images of one another. So P being a mirror image of A, with the line through lowercase q and uppercase q being the mirror. And so if q is moved very close to uppercase q, if lowercase q is moved very close to uppercase q, what we see is that now we do have a tangent at point Q that creates a mirror image. Creates a mirror image, so you have two images. We have an image on point P, which is on the base circle, and we have an image of that on the cardioid. So what happens is that the tangents at all these points that are coincident on the base circle create images that would be cardioid. This is very interesting. So another way of looking at a cardioid is a set of mirror images of points on the base circle. They end up forming a locus, and that is the cardioid. So that's a very interesting way of actually viewing it, right? So let's continue with a few other things along the way. So now let's continue with that in mind. So what we'll now find out that we can have a secondary circle that is rotating around the base circle, and we have a fixed point. We have a fixed point that is on that secondary circle rotating around the base circle, and the path taken by that point is our cardioid, right? So, which is a very interesting way of also looking at it. So our cardioid has many ways of looking at it. When you have a secondary circle rotating around the base circle, creating a locus or a trajectory that is also a cardioid. So that kind of sums things the way we want to look at it. But let's continue a little bit more and look at some of the properties of the cardioid. So previously we looked at our base circle. So this is our base circle, right? And so we do have point Q. This point Q has a tangent and we saw that this tangent will have a point A on the base circle that has a mirror image against the tangent at point P. So the cardioid P is a set of or P is on the cardioid that is created by this base circle. Similarly, we have point Q prime, right? And Q prime would have a tangent, and would see that Q prime also has an image of point A on point P prime. So point P prime also is on that cardioid. And if Q prime and Q lie on this line that passes through the center O, so this is our center, we are going to look at some of the properties that are very interesting to this relationship, right? So this is our radius, this is our radius, this is our radius, this is our radius, right? So let's continue and see some of the very interesting properties, right? So we assume that this is our angle theta, and this, since this is a straight line, we have the remainder of the angle being 180 minus theta, right? And so since this is the same as this, we're going to have theta over 2 here and theta over 2 there. And since this is r, this line here is going to be r sine theta over 2, and this line is going to be r sine theta over 2. Similarly, this is going to be 90 minus theta over 2, and this is going to be 90 minus theta over 2. But since this is the radius, we'll see that the part of the base here is going to be r cosine theta over 2, cosine theta over 2. Now, since this angle here is 90 minus theta over 2, this angle is going to be theta over 2. And since this is a tangent, this angle is 90 degrees, so this angle is 90 degrees. So similarly, what happens is this angle here is going to be 90 minus theta over 2. So that if we do have r cosine theta over 2 plus r cosine theta over 2, we have 2r cosine theta over 2. Similarly, here we have 2r sine theta over 2. We are going to prove that the distance P and P prime is 4 times the radius of the base triangle. Okay, so let's continue. We've already demarcated that this is 2r cosine theta over 2, 2r cosine theta over 2. And we know that this is 90 degrees, this is 90 degrees. And this is 90 minus theta over 2. And since this is going to be 90 minus theta over 2, and this is a tangent, this is going to be theta over 2. So we're going to see that this line there is going to be 2r sine square theta. So 2 times 2 is going to be 4r sine square theta. And so is the line from here to this line. So P prime is going to be equal to AM, right? I mean AP, sorry, plus AP prime. And AP is 4r cosine square theta, whereas AP prime is 4r sine square theta, using the rules of trigonometry, or sine square theta plus cosine square theta is equals to 1. We see that P prime is 4r, or 4 times the radius. So that is point number 1. We have shown that P prime is equal to 4r, and that is 4 times the distance, the radius of the base circle. Okay, so let's continue. The next thing we would like to show is that PQ, in other words, this from P is this, meets this PQ emits PQ prime at point R. That's the right angle. We need to show that. And that we can show if this is an angle phi, this angle should be 90 minus phi, so that the triangle PP prime R is, these angles are going to add 180 degrees. And by showing that, we should be able to prove that they meet at right angle. So let's go ahead and do that. We've already shown that this is theta over 2 and this is 90 minus theta over 2. So obviously this is going to be 90 degrees, right? So P, Q, and P prime, Q prime meet on the base circle at 90 degree. Okay, so what does that tell you? It's very obvious as well that the angle subtended at the center is twice the angle subtended at the secondary. So since this is 180 degrees, it is also obvious to note that this is 90 degrees. That's also another way of looking at it. So very, very obvious. Another property that is key is that the midpoint M here of P prime is on the base circle. So we just have to show that this part is the middle point. It's easy. What you'll do is you could draw a triangle here, and the distance here can be shown to be equal. So MP prime, MP, those can be shown to be equal very easily. I will leave that for you to figure out, or you could even draw a line like that and use geometry to show that those MP and MP prime are equal. So that's one other thing. The other thing also to show is that the tangents to the cardioid at P and P prime are at right angles, and the locus of the intersection is a circle. So what that means is that if we have the circles, one that is centered at Q and the other one that is centered at Q and the other one centered at Q prime, the tangents at P prime and at P, they meet at a right angle. That's easy to show. So this angle here is 90 degrees, and it's because this is also 90 degrees. Very obvious, but there's also another property that is worth having in mind. Let's do some other important thing. So let's assume that this is a point on it, the center point, right? And then we're looking at the cardioid. The cardioid is passes point P, passes point P prime, and let's look at the angle theta being the angle at A. That's our center, and the base is AB. We know that AM, where M is the mid point of P prime, we know that AM is 2R cosine theta. 2R cosine theta. This is R, and like that. So this is 2R cosine theta. And AP is AM plus MP. Since this is midpoint and we saw that PP prime equals to 4R, therefore MP is going to be 2. In other words, if we have theta as the angle of the segment that joins the center we've taken of our cardioid, that is A, to any point P on the cardioid, the relationship, if we call this our radius of the cardioid, is between the radius of the cardioid, the radius of the base circle, and the angle theta is as shown here. Okay. Another way of looking at the cardioid, as we demonstrated, is that you have two circles. We have the base circle here, and we have another circle that is rotating around while rolling, and we get a fixed point P, the locus defined by point P is the cardioid. Similarly, if the base circle is kept stationary and we do have this external circle that is rotating while rolling around the base circle, we could pick one point P, and that the path taken by P is also a cardioid. So there are a number of ways that we can define a cardioid. A cardioid is obviously a set, it's an envelope created by a set of circles whose center points equidistant from one another of radius that spans a distance from that center to one given point on the circumference of the base circle. And a type of curve that is created like that is called a pedal, right? But also we saw that this cardioid is a curve that is created when you have a circle that is outside another circle rolling, and we have one point fixed, and that could be looked at as an epicycloid where the two circles are of the same radii. We've also looked at this situation where we have a circle outside rotating around the base circle, and we see point P. So there are a number of definitions. We saw a cardioid as a pedal of a base curve, the circle. We also saw that it can also be a conchoid of a circle relative to a point on its circumference. And we'll look at what the word conchoid means shortly. We know what an epicycloid is, a circle created, a point created, a set of points created by another circle on top of another circle. So a cardioid is an epicycloid where the two circles are of the same radii. Therefore, it's a locus of a point on the circumference of a circle which rolls around the outside of an equal fixed circle. We also saw that a cardioid is a locus of a point on the circumference of a circle rolling on a fixed circle of half its radius, the fixed circle being inside the rolling circle. So a couple of other things that is worth noting is that you've probably looked at microphones. People will tell you, oh, This is a cardioid microphone. Why? Because the intensity, the sensitivity on this side is more than on the other surrounding points. So it's effective in that way. You've heard of a super cardioid microphone. You've heard of a hyper cardioid microphone, really deriving from the shape of the cardioid. This also just a quick summary of what we've talked about. There's a cardioid microphone, a super cardioid, and as you can see, the sensitivity of these microphones as a function of the angle, this azimuthal angle is shown here. So that's just a quick application, real-world application of the shape cardioid. So if next time you hear somebody talk about a cardioid or a cardioid microphone, at least you would know. So until next time, I hope you enjoyed. Have a great time or a great day ahead. Bye-bye.